The purpose of this video is to kind of tie things together with the chi-square test of independence and chi-square goodness of fit. Now, I think the reason I created this video, well, I don't think the reason I created the video, the reason I know the reason I created the video is, historically when I've taught this chi-square techniques to my students, ranging from undergrad to grad students, math majors, people working on masters in mathematics. Uh, there seems to be some confusion, so I thought, well, if we kind of go out with a bang and compare the two in one example, maybe it'll make a difference. I don't know. And also, I think the very most, or the very most, oh my goodness, the most important thing is I'm going to show you how to write up a chi-square test of independence. So the data set that I have opened up into R, which you'll have access to, is called falls and canes. And there's a lot more going on in the data set than just falls and cane. Patients reporting falls and patients reporting cane use. Upgo, reactor. We've seen this before. We can see that the sample size is 244. Again, I can find the sample size by just taking length of any of the variables. The very first thing I do is I force fall status and I force cane to be factors because those are the two variables that I'm going to be using in my first illustration. So what I want to do is I want to look at the relationship between fall status, a fall status either reported as yes or no, and not to be confused with fall group, which reports as none, one or two, or multiple falls. So I'm looking at the fall status, yes or no. The cane use, yes or no. So our null hypothesis is that fall status and cane use are independent, they're not related. Our alternative hypothesis is that fall status and cane use are related. So they are dependent. We'll get to this stuff a little bit later. Now, I want to show you the way that I would write this up, and let's go through. This is just an FYI. You wouldn't include this in your write-up. But what I would do if I was going to analyze fall status and cane use is I would say that the cross-tabulation of fall status by cane use showed that the proportion of those who fell and reported a cane. So I've got the table right here. So those who fell and reported a cane use were 35 out of the 244. So that's 14.3%. And that turns out that it's quite different than those who reported a fall. Yeah, right there. And did not report using a cane. So it's almost double, not quite, but almost double. So I'm going to run a chi-square test of independence, which I do right here. And I should actually, I should say this, a chi-square test of independence using using Yates continuity correction method indicated no significant association between fall status and using a cane. So again, I have my degrees of freedom 1, my test statistic is 0.95, which I've reported, my p-value is 0.33. So circling back to the null and alternative hypotheses that I gave you earlier, we do not reject the null, so we assume that these two are not related. Next thing I'd want to do is I'd want to report the odds ratio. And if you use, again, remember you have to access the install package. I've already done that, so I don't have to, daggone it. I'm in Gmodels. ggplot is actually something different than I use, but Gmodels is what we need to use in this situation to be able to use the cross table command that I have illustrated before. To get what I need to have Fisher equal true and chi-square equal true, and then format equal SPSS in quotation. So I can come down to the cool stuff, again, continuity correction right here. And the sample estimate for the odds ratio is 1.36. The confidence interval, 95% confidence interval, is 0.76 to 2.45, which I have reported. And then I just interpret that the odds of a patient reporting a fall and reporting the use of a cane are 1.36 higher than the odds of a patient reporting a fall when reporting not using a cane. Now, just an FYI, you wouldn't put this in your write-up, but again, I'm still kind of teaching. This 1.36 comes from 35 over 40. So what I do, first of all, it's the odds of falling using a cane. So I have the count of falling divided by the count of not falling, so 35 over 40. And in the bottom I have non-cane use, but I still report the odds of falling versus not falling, 66 over 103. So this is where the 1.36 comes from. That's really, really easy to get using the cross table command. And again, if you're not following along these videos, first of all, shame on you, but if you're just kind of, jumping around trying to just find something that aligns with the homework problem, you may not have installed the package G model. So if you do, then this isn't going to work, but that's on you. I illustrated that in a previous video. All right, so let's go back to the original. So let's shift gears to the chi-square goodness of fit. So let's say that some theory or national study claims that for the elderly, the 10% report multiple falls, 60% report no falls, and 30% report 1 or 2 falls. So multiple falls would be 3 or more in this context. And these reports are within the last 30 days. So a researcher would like to compare the fall counts in this sample data that I have in R to the claims made in the national study. So the null hypothesis would be that the percentage with multiple falls, that's what MF stands for, is 10%. The percentage with no falls, that's what NF is in this context, is 60%. And the percentage of those with 1 or 2 falls is 30%. The alternative is at least one of these are different. So the first thing that I would want to do in this context is I would want to get the table of the fall groups where I have, it's another variable where I have all 3 categories of falls, multiple, none, and 1 or 2. And so those are my observed cell counts for the sample data. And then I can go into the proportion. So the national study says 10% report multiple falls. Our sample data is 10.7. Okay, pretty close. None is 60%. Our sample data is 58.2%. Again, pretty close to the national claim. And 31.1% versus 30, pretty close to the national claim. But you have to be really careful in comparing sample data to population data and let the process play out and make conclusions from there. So again, from the previous video, I type in the observed cell counts. Unlike StatCrunch, the expected are the percentages, 0.10, 0.60, 0.30. These must add up to 1 again. And then you can run the chi-square test on X. And it's sometimes, I see students right here put Y equal, but the command in R has to have P equal EXP. So we do not have statistical significance, so this comment, the null hypothesis is more believable. So we conclude that there's no reason to feel that the percentage of fall categories in our sample data differs from the national study claims. All right, gang, that's all I got. That will wrap up lesson 4.